Okay, we're going to talk about integrated rate laws and specifically how the concentration of the reactants depends on time. So from Chem 116, you have seen log of A as a function of temperature, or sorry, as a function of time is linear when you plot the log of A. 1 over A is linear, and then A is linear with T. And this designates first order, second order, zeroth order. And you were just supposed to memorize like, oh, that makes perfect sense. That you plot them in different ways, and that seems weird. Well, hopefully it won't seem weird after this because we're going to derive why we have these three different versions. And I hate to tell you, there are a lot more, so many more. Okay, cool. So let's start with first order because I think it's the easiest one to approach. Okay, so for first order, A goes to products. We don't care about what happens on the product side. We just care about the reactants, and we're looking at the rate of consumption of A. So the rate of the reaction is equal to the rate of the consumption of A, which is equal to minus dA dt, and that's equal to the rate law, which is the rate constant times the concentration of A. Rate law. Actually, I guess this is the rate law. If there's a K, that's the rate law. Okay, we can also rearrange this and say that if we then add dA dt to the right-hand side, we get 0 is equal to dA dt plus Kr concentration of A. Go team. This is a differential equation. I'm not quite sure in Math 155 if you were introduced to differential equations, but the idea is that A is a function of T. So that the concentration of A is function of T, just like f of T. So you have some function that says as time changes, your function is going to change. So as time changes, there's going to be, if this is first order, there's going to be a decrease in the rate at which A disappears. Now, if you know me at all, you know that I cannot stand curvy lines. I want to make everything nice and linear because linear trends are easier for us to, one, say that, yes, they are in fact linear. I could think of like 3 different equations that could fit this, all very different. And it's hard to extract useful information if you don't have a linear trend. So the goal of a differential equation, so this is a differential equation, is to find the function A is a function of T, such that if you take the derivative of it and then add Kr times the original function, again, this is A is a function of T, and you add that together, you get 0. Okay, so there is a solution which is a function. So the solution, or I'll say the answer to this, what we call, differential, so diffie Q. So the answer to this differential equation is a function. Okay, we're no longer looking for numbers, we are looking for functions. And that function, if it satisfies this equation, bingo, that's our function. Cool? Okay. Okay, so now I've got dA dt plus Kr concentration of A is equal to 0. And again, these are functions of time. So, and I might slip and say temperature a bunch just because I'm so not used to dealing with time-dependent functions. I'm so used to dealing with T as temperature. So please forgive me. If I say temperature, I mean time. Okay, so I'm going to show you how we solve this fully using a method of solving a differential equation. I am not expecting you to be able to do this. I don't want you to do this for any of the other functions, but I want you to have this experience so you have an appreciation for what are boundary conditions, how you set up limits of understanding the conditions of the reaction, and just the way that we solve differential equations in general. Most of the time, it's a guess and check method. You guess it and you see if it works. This will also serve you well when we get into quantum next term, if you are pursuing that with me. All right, so at T0, so at 0 time, the concentration of A is equal to the initial concentration, okay? And the concentration of the products is equal to 0. At a later time, and I'm gonna say T equals T. It might seem confusing, but I don't care what this time is, 5 minutes, 10 minutes, 1,000 years, don't care. It's some later time. My concentration of A is equal to the concentration of my initial A minus some value. It's been consumed. I've lost a little bit. And that little bit that's been lost has gone into the concentration of my products. Okay, so we're going to start with the rate of the reaction. So dA dt, and I'm actually going to make this dP dt, even though I said we don't really care about the products, because I want this to be a positive value. The rate of formation would be positive, whereas the rate of consumption would be negative. Is equal to K times the concentration of A. Okay, so now I'm going to just impose this X and this A0 minus X into this relationship. So I'm going to say dx dt is equal to K times A0 minus X. Okay, so what I've done is I've now combined P and A into a single variable, X, with A0 being a constant. This is just the initial concentration of A that we start with. So we know we start with 10 moles per liter. Cool. A is going to disappear, and that's going to decrease over time in terms of this X. Okay, so now some fun math. Notice I have a dx. And let me back up a second. If we find how this X depends on time, that means that we find how A depends on time, which is the goal of finding A as a function of time, the solution to our differential equation. Okay, so I'm going to take this and solve it. Okay, I've just rewritten it to make it a little easier. So I'm going to now move this X to the left-hand side. A0 minus X is equal to K dt. So I've just took this down here, move that upstairs, integrate both sides. And I'm going to say I'm going to integrate this from X equals 0 to X equals some other X. And I'm going to name that X prime. There are going to be a lot of different types of parameters. And so you'll see a common habit is to just say it's the same parameter, but I'm just going to make a prime to designate that it's a slightly different one. So X changes from 0 to some other X value, and T goes from 0 to some time T. Okay, so T equals 0 to some time T. Okay, so now I am going to integrate the rate law, which yields the integrated rate law. So this becomes minus log of A0 minus X, evaluated from X equals 0 to X equals some X prime. And then this equals K times T, integrated from T equals 0 to some later time. All right, so if I now impose, so hopefully you can see, I can do a U substitution here. And I can say U is equal to A0 minus X, such that du is equal to minus dx. And then that's where this negative sign comes in. And then this then becomes integral d, so with a negative sign, du over u, which is just negative log of u integrated over the integration limits. Cool. So thermodynamics does help us a little bit from that mathematics that we've done, but we're using this in a very different way, trying to find the function that describes how this is true. And that function is the function of A, which will come in a second. Okay. So now let me impose these integration limits. Okay, so I've got minus log A0 minus X prime, minus A minus, so that's going to be a plus log of A0 minus 0. Cool, so that notice that this is a minus, actually I'm going to write that in, minus A minus. So it's minus log here, but because I'm taking the integration limits, it's going to be initial minus final, or sorry, final minus initial, is equal to KT minus K times 0. All right. So if I go back to my, so let's simplify this a little bit. If I go back to my original idea of what am I defining as A, well, that's just A0 minus some quantity of A that has been consumed. And so if X prime is the quantity that has been consumed and has become my products, this whole thing just becomes log of the concentration of A. So I'm left with minus log concentration of A plus minus minus A0 minus 0 is A0 plus log concentration of A0 is equal to KT. Cool. So now what I'm going to do is I'm just going to move over this negative sign. Let's come over here. And I'm going to get log of A is equal to minus KT plus log concentration of A0. Awesome. So if I were to plot this as a log concentration of A as a function of time, I get a linear trend with the slope equaling minus K, whoops, minus K. And then I get right here, log of A0, the concentration, the initial concentration that I have at time 0, and I shouldn't do that because it doesn't make any sense for there to be a concentration prior to t equals 0, is equal to the initial concentration that I have. This is our integrated rate law that is related to our rate law. So rate law, integrated rate law, first order. First order. Yay. Okay. Cool. Oh, okay, let's go back again. So let me erase all of this. Integrated rate law. But I didn't actually tell you what my function was of A with respect to time. I've got the linearized version, but let's unlinearize this to see what that actual function is. Okay, I've got log of A minus log of A0 is equal to minus KT. I've just moved the y-intercept log of A0 over to the left-hand side. All right, I'm going to take the exponential of each of these. This is the E. This is also known as Napier's constant. So if I take e to the logarithm, actually, before I do that, I'm going to take this and turn this into exponent log of the fraction A over A0. That'll help show some of the stuff that we're doing. Okay, so if I do this, that gives me the exponent of the logarithm gives me the fraction of A over A0 equals e to the minus, KT. And then if I move the initial concentration over, now I have my function, A as a function of time, is equal to the initial concentration times the exponent minus KT. So if we go back to the original dA dt, this was from the rate of the equation, plus KT equals 0. If I were to take the first derivative of this with respect to time, I get A0 e to the minus KT times the derivative that's up here times a minus K plus, oops, that's not KT, I'm so sorry. That should be K times the concentration of A. Multiply this by K times my function for A, which is A0 e to the minus KT. Look what I get. Negative KA0 e to the minus KT plus KA0 e to the minus KT equals 0. Check. So now I have a function, the solution to the differential equation, that satisfies. So if I take this function and put it into this equation, this statement is now true. That's a solution to the differential equation. Okay, so that's how we get the integrated rate law and how you would determine all of the different types of integrated rate laws for the various types of chemical reactions you can have. So I'm going to stop here and I'm going to share my screen and show you the solution to all of the different types of equations, and just so you can see how complicated this gets. Okay, so this is table 17B.3, the integrated rate laws. So here is the reaction that we just did, which is first order, A goes to products. Here is my rate law. Here is my integrated rate law, which if you were to extract the A0 and A, you would get the linearized form that you can plot and see clearly the y-intercept and the slope. Okay, let's look at a second order reaction that follows this rate law. If you were to go through all of the steps, find the differential equation, find the solution that satisfies that differential equation through an integration or through various other techniques, this is the rate law that you would get that is now both dependent on the product's value and the initial concentration, or you can simplify that to be the concentration of A is equal to this ratio. You can go even further. If you have a second order that is not just about two A values, but it's an A and a B where A and B are different, this is your integrated rate law. And let's keep going further. For third order, which are very rare, you would have A plus 2B yielding products. And so this is your rate law. Check out this bad boy. So this would then be the integrated rate law. So if you were to want to find that function of the concentrations dictating your rate law, what is their time dependence, this is what you would find. So you can see that it's becoming more and more complicated, which is why we're obviously not going to go through and solve each of these, but I want you to appreciate the work that goes in, number one, the complexity of reaction rates. And this is where I get to throw out this wonderful bit. Ask Deanna about this. So Deanna is an atmospheric chemist who studies kinetics of atmospheric reactions. And so for her dissertation, I believe it was 2 numbers, maybe 3. I'm not quite sure. It's 2 or 3 K values for very specific reactions. So her whole dissertation was really just finding those 3 values, which required her to determine the rate laws and understand all of the different aspects that go into what is that function of time for that concentration of the reactants that she was working with. I think it was actually it was some sort of methyl or mercury reaction. I don't remember the specifics from her dissertation directly, but 6 years to determine 3 values of these Ks. This work is very challenging because of the complexity of the chemical reactions once you move past a simple elementary first order reaction. Go team? Okay, stop share. Next plan. I want to show you real quick second order, and then we'll move on to half-lives. Okay, so for second order, we have A plus B yields products, or we have A plus A yields products. So the rate of consumption, the ADT, is equal to K times the concentration of A times the concentration of B, or you could say the same thing, minus dA dt is equal to KA squared. Okay, so likewise, you would say minus dA dt, actually I'm going to make this a plus K, minus A B is equal to 0, and then you would solve, go through all that process to solve to get the integrated rate laws or the solutions to the differential equations like I showed you in that table. If you do the same thing for here, where you only have 2 A's and not the AB, you would end up getting, as the final result, 1 over A plus, oops, I always get the negative signs wrong here, plus KT plus 1 over A0. So 1 over A is equal to positive KT plus 1 over A0. And if you were to plot that as 1 over concentration of A versus time, you would get a positive. So here, 1 over A0, this is where you would determine your initial concentration, or you would start with that data because you would know what you had. And then the slope is then equal to your rate constant. And you can see how if the slope changes, so if this is a really steep line, you have a really large rate constant, really not so steep line, you have a low rate constant. But this is where the 1 over A term came from, again, that solution to the differential equation. Cool. And if you were to plot this one, it would be slightly different because you would have both a contributing A and B. So it depends on how you're looking at your reaction. No longer would you just have one plot of data to determine your rate constant. Now you would have 2, or the relationship of both of those. Cool? Okay, I'm gonna pause and we're talking about half-life.